Hello and welcome to another video tutorial in which we will be having a closer look at a GPIOs, which are general purpose input and output of a microprocessor. Typically, these microprocessor chips usually have these pins, and some of them are so-called GPIOs. Those are the pins which do not have any pre-assigned function, and it is left up to the programmer to decide what should they do. Now, before we start, I would just like to remind ourselves that we will be working with something called positive logic, which means that whenever the output voltage or an input voltage of some pin is close to 0 volts or so-called ground, we are talking about logic low. And if the output or input voltage is close to the supply rail or equal to the supply rail, we call that VCC often, we are talking about logic high state. These input and output pins can either be digital or analog, so that is a very important distinction, digital and analog. Now, a digital pin can basically only process voltage which is very close to the supply rail or very close to the ground rail. So that means it can either be 1 or 0. It can either be logic high or it can be logic low, but it cannot be anything in between. Now, analog, on the other hand, looks a bit different. Analog can basically process any voltage that is between ground and all the way to the supply voltage. In some cases, this is not necessarily true. In some cases, they may be only able to process some interval which is in sort of between the ground and the positive supply voltage. Now, analog pins, let's talk about them first. Analog pins, they usually look sort of like this. Let me just grab different size. Analog pins usually look like they have a very, very high impedance or very high resistance on the output. This would be the analog pin. So we can call it, for example, A0 as zeroth pin that is in analog configuration on the microprocessor. There can be several of these pins. There can be A1, there can be A2, and so on. And so this is one of those pins, and they usually have very high output or input impedance. So that means this resistor that sort of models the impedance will have a very, very high resistance, typically over 1 mega ohm. So a very high impedance, you could not ever drive anything from this pin because the impedance is very large, that anything that you connect to this pin will have a very, very high will act as a very high load, and it will destabilize the voltage that we see on the analog pin. Now, usually these analog pins, they can either input a analog voltage or they can output analog voltage, meaning that they either have something which is called an ADC, which is analog to digital converter, or they have something we called a DAC, which is a digital to analog converter. Now, these are important because, of course, the microprocessor itself is a digital device. So if you say to the output pin of the microprocessor to have some kind of voltage on its output, what you are actually doing is that you're using the digital to analog converter first that takes all those, ones and zeros that the microprocessor is feeding and converts it to some voltage, let's say 2.31 volts or whatever. Now, if you're doing the opposite, if you have an analog voltage on the input, well, then you are feeding some kind of voltage over here, let's say 2.33 volts or whatever voltage. And now the microprocessor, to understand it, needs this analog to digital converter, which will convert this analog value to some ones and zeros that the microprocessor um, can distinguish. So as I said, the output impedance over here is usually very high. which means that if you ever want to power anything from this circuit, then you will most likely see a failure because this output impedance is just too high. So for example, if you wanted to connect an LED like so, this LED will never ever light up. So what we have to do, and some microprocessors have this already integrated, is that they have some sort of buffer, which is usually just an operational amplifier, which is connected as a voltage follower. So it's connected sort of like this, where here you have the plus and here you have the negative sign, and it looks somewhat like this. Now, this operational amplifier, what's it going to do is that whatever voltage is on here on the non-inverting pin, the same voltage will be here on the output. However, it will be significantly boosted in the current. While this pin on itself had like 1 mega ohm impedance, this operational amplifier will have significantly lower impedance. Uh, it could be like tens or hundreds of ohms, which is enough to power some circuits that could be driven from this pin. Some microprocessors, as I said, basically have this buffer already integrated into the microprocessor. Some of those may not necessarily have to be activated. You may have to configure the pin to use the buffer or to disable the buffer. So here you can see exactly what I'm talking about. This is a data sheet of an STM32L151, which is a microprocessor that I have been working with recently. And in this case, there is this output impedance without the output buffer, and it claims to be 16 kilo ohms, around 16 kilo ohms. So that's way less than the 1 mega ohm I was talking about before, but it is still very high impedance, right? You couldn't really power any circuit from 16 kilo ohm impedance. So you need to turn on the buffer in case you ever wanted to deliver sufficient current from the digital to analog converter. I haven't been able to find information about the output impedance with the buffer on, so it's not written in this datasheet, unfortunately. Over here, you can see that the digital analog control integrates output buffer that can be used to reduce the output impedance and to drive external loads directly without the use of operational amplifier. And the buffer can also be disabled by configuring some bit in the register, right? So you don't have to use this buffer. You can use it, but you don't have to. And over here, I've placed this piece of code. This is just an example piece of code that you can use to configure a digital to analog converter of this STM32L microprocessor. So it's important to notice here DAC output buffer disable. So in this case, it would be disabled, meaning that there would be no operational amplifier connected here. Uh, in the microprocessor, it would be sort of bypassed and disconnected. It wouldn't be here. Back in the datasheet, we can actually see one quite troubling thing, is that the output voltage range is not the same with the buffer on and with the buffer off. So with the buffer off, it means that the output voltage of the digital analog converter can be set so that it is anything in the range from 0.5 millivolts all the way to pretty much the positive supply rail. However, if we turn the buffer on, well, then the situation drastically changes. It is now only configurable from 0.2 volts to the supply voltage rail minus 0.2 volts. So that means if we power the microprocessor from, let's say, 3.3 volts, then the DAC is only able to output voltage from 0.2 to 3.1 volts. So the range drastically changes, and that can or cannot be a problem, depends on your application. But of course, if you wanted to provide sufficient current and to generate, in this example, generate, for example, 0.1 volt, well then you would have to turn the buffer off and then add an external amplifier after the pin. So you wouldn't use any internal amplifier, but you would connect another amplifier here, some amplifier that can actually work with your desired voltage range. A very important issue is the voltage supply itself. We usually power the microprocessors from low voltages like 3.3 or 5 volts, but the most important thing is that this voltage needs to be very, very stable and very precise. And the reason for that is how the ADC and how the DAC actually works. Let's have a look at how ADC in principle, how does it work? So suppose that we have some analog voltage over here. This is some analog power supply, which means that it can give off any voltage. So let's say we have 3 volts here. And now how do we decide how to convert this voltage to a digital value? Well, we could do such thing that we will have a comparator here, just like so. And we will feed, for example, 2.5 volts over here. This is some voltage reference, some stable voltage reference. We can tell that this is 2.5 volts at all times. Now, the output of this comparator will tell us if the voltage is higher or lower than 2.5 volts. In case it is higher, we will have a logic 1 or high on the output, and if not, then there's going to be logic low. Of course, this is going to be logic high at all times because these 3 volts will always be bigger than these 2.5 volts. Now, this is a very crappy analog to digital converter because it only tells us if the sampled voltage is lower or higher than 2.5 volts. But what we can do is that we can add a lot of these comparators, connected them all in sort of parallel. Let's have another one over here. And we connect it such a way, and we bring different voltage references to these non-inverting pins. So we have 2.5 volts here. Let's bring 3.5 volts here. Let's bring 1.5 volts here. Well, now we've increased the resolution of this analog to digital converter because now we can tell that the voltage is not only higher than 1.5 volts, not only higher than 2.5 volts, but we can also say that it is definitely not as high as 3.5 volts. So you can see that we're getting more of these binary digits and that the resolution of our ADC is becoming better and better. Right now, the resolution is 1 volt because we can tell the difference between 3.5 volts and 2.5 volts. So 1 volt resolution would be very crappy for an analog to digital converter. So what's actually happening in analog digital converters is the same thing, but we have many, many more of these comparators. We have thousands of them. And this way, the resolution of the ADC gets higher and higher. Now, the problem is that these references, they have to be very stable. Like if there is 2.5 volts here, we must ensure that there will be 2.5 volts and nothing else. There cannot be any voltage ripple. There cannot be any oscillations. This voltage must be very, very stable. The same goes for this 3.5 volts and this 1.5 volts. And so these voltage references, they are usually made out of the supply voltage, because if we have a supply voltage over here, let's say it's 5 volts, so this is our supply voltage VCC. How do we create 3.5, 2.5, and 1.5 volts? Well, we can do that quite easily. We can create voltage divider, and we can set the resistances such a way that we have 3.5 volts here, 2.5 volts here, and I've missed one resistor, of course, and that would be over here, 1.5 volts, and another resistor to ground. just like so. So these resistors, they are not going to introduce any voltage ripple. They only divide the voltage, they do nothing else. So we must only ensure that the supply voltage is very, very stable, because the stability of the supply voltage will then determine the stability of these voltage references, and therefore it will also affect how sensitive or how precise our analog to digital converter is. Now, what I've done in this simulation over here is that I have a comparator to which I feed 2.501 volts, and then I power it from 5 volt supply. You can see the 5 volt over here. It's nice and stable 5 volts. And I have a voltage divider which divides the voltage by 2 because these resistors are the same value, meaning that we will have 2.5 volts here. So the voltage on this pin is going to be just teeny tiny little bit higher than the voltage here, right? 1 millivolt higher than the voltage here. And that means, since this voltage is on the non-inverting, sorry, on the inverting input, that means that we expect that the output voltage is going to be 0, because the voltage over here on the inverting, sorry, on the non-inverting input is lower than the voltage on the non-inverting input. So let's have a look at the output. We expect nice 0. And what do we see? Well, we see these sort of oscillations. We see that the voltage is nowhere near stable 0 volts. So why is that the case? Well, it's because when I said that we have nice 5 volts on the supply rail here, I actually lied, because if we have a closer look at the supply voltage, we can see it's not actually that nice. It's not nice at all. We have these sort of this voltage ripple. So on a large scale, it may look like the 5 volt is nice and stable, but if you zoom closer, well, we can see that it is not as good. So as we have seen, it is absolutely crucial that we power our microprocessor from some very stable voltage, meaning that it cannot ever be powered from a switch mode power supply, because switching power supplies create a lot of EMI, or electromagnetic interference, and that is going to cause all sorts of trouble, especially if we are using the analog features of the microprocessor. So we usually want to power microprocessors with linear power supplies or batteries, and this usually renders much better performance. And even with linear power supplies, you may want to, or actually it's always done, that there is a capacitor over here between the positive supply rail and the ground. We call this capacitor, or we call it bypass capacitor or decoupling capacitor. And it is very important because even from a linear power supply, there can be all sorts of transients and interference that may not be as huge as from a switch mode power supply, but there can be some small oscillations, something that you just do not see. And so it's always preferable to have a to have a capacitor over here. Also, it protects you from interference from other traces on the circuit board. You may have a microprocessor which is powered from a linear power supply, and then very close next to the microprocessor, you may have a switch mode power supply that powers something else. Now, this switch mode power supply is going to cause interference in the voltage from the linear power supply as well. So that's why we add capacitors on the positive and negative rail of the between the positive and the negative rail of the microprocessor's power. And we usually add one capacitor over here, which is typically 100 nanofarads, which is just a very common capacitance for this purpose. And sometimes we also add another capacitor in parallel, and this one usually is a bit higher in value, let's say 1 microfarad or perhaps even 10 microfarad. Now you may ask yourself, why don't we just use one single capacitor that's going to have a higher capacitance? You know, it can have both these capacitances combined. Instead of these two capacitors, we could have just used one capacitor with 1.1 microfarad. That would give us the same equivalent capacitance as these two in parallel. Well, but that's not going to work very well because different capacitance capacitors behave different at different frequencies. So while 100 nanofarad capacitor is going to be excellent at suppressing very, very high frequency voltage ripple, 1 microfarad may not do as good of a job. And vice versa, if we're talking about smaller frequency ripple, then the 100 nanofarad is not going to do a very good job. So this is why instead of one big capacitor, we are splitting the capacitance into multiple capacitors like so. Usually you will see 100 nanofarad at pretty much every supply rail of every chip that you see on every circuit board. And if you really want to have the voltage as EMI proof as possible, you also put a 1 microfarad or a 10 microfarad or just a higher capacitance over here. Sometimes you may also see that we also add another capacitance over here. Let's say 10 microfarad or so. And then what we do is that we also add an inductor. And I have erased this. Okay, we add an inductor over here. So this acts as a sort of low pass filter, uh, this inductor together with these two capacitors, and this further diminishes the EMI problems. So not only there are some rules to which power supply can we use to power microprocessors, but there are also some design rules when we design the PCB or when we design the schematic. So let's have a look at this one, as we've already talked about, the STM32L151. So this is the pinout of the chip, and immediately we can see these pins VSSA, that is the ground pin, and VDDA. So sometimes they call it VDD, sometimes they call it VCC. This is the positive supply rail. And what we can see is that we have multiple of these. We have VDDA, here's VDD1, here's VDD2, there's also VSS2, which means another ground pin. So there are multiple of these power pins, and we must make sure that the design kind of uses them all, ideally, and that it uses them in a sort of proper way. When designing a PCB, we need to make sure these are decoupled by capacitors. So let's have a look at one schematic that I've made recently. This is a schematic that's using an STM32L151. So you can see both of these ground pins are, of course, grounded. And all of these, which are the positive supply rail pins, they are connected to 3.3 volts. But there is a very important thing over here. We got 1, 2, 3 100 nanofarad capacitors, each 100 nanofarad capacitor for each of the VDD pins, and one common microfarad, 1 microfarad capacitor in parallel as well. Now notice there is this VDDA pin. VDDA stands for analog, VDD for analog pins. So digital and analog pins have split voltage supply rail. Now this is very important because we don't care that much about stability of the input power voltage on the digital pins, but we very much care about that in the analog, as we've already seen before. So we don't have to make sure that this digital pins, this power supply for the digital pins is as stable, but we really need to make sure that the analog voltage rail is very, very stable. So we got 100 nanofarad capacitor bypassing it, and we got 1 microfarad capacitor in parallel, also as decoupling or bypassing capacitor. And here we got what I've drawn before. We've seen we had a capacitor, inductor, and another capacitor. Well, this is pretty much exactly it. We got the positive supply rail, 3.3 volts. Then we got quite big capacitor, 10 microfarad. Here we have, this is called a ferrite bead, and it pretty much acts as an inductor. So we got capacitor, inductor, capacitor, and another capacitor. So this is just a better filter. So this analog voltage rail is better filtered. So now let's have a look at the PCB, which I've opened over here. So this is the PCB. Here on the top side is the microprocessor, and on the bottom side are the capacitors. They are on the bottom side because then they can be closer to the pins themselves, right? So notice how these capacitors are placed. So they are placed to be as close to all the digital pins. So if we have a look on the bottom side of the PCB, we see we got 3.3 volt connected pin over here. That's why a capacitor is very close. And we got another over here. And here we got the capacitors. There is another here. And again, capacitor right below the pin. So this is very important that the capacitors are as close to the pins as possible. So that's why on the top side of the PCB, we can see just this one little capacitor over here, but on the bottom side we can see all of it. So these are the capacitors, and this is the ferrite bead, the inductance pretty much, and these are another capacitors. So they need to be very close to the microprocessor itself. So there are a couple of things about the analog which I would like to discuss before we move along to the digital. So first of all, if we have analog pin, it doesn't necessarily mean that the analog pin can output and input analog voltage. Usually, when we have a analog pin, it means that it can process, it can input analog voltage. So here is the pin descriptions of the STM32L151. We can see these are the pin numbers over here, this left column. And here are the main function of the pin and alternate function and additional function. So these are the functions that can be configured for the pin um, to process. So for example, pin 15, PC0, can be used as an analog pin, meaning it has an ADC, so it can input, it can process analog voltage, but it doesn't have DAC, so it cannot output analog voltage. Actually, what you will find that most of these analog pins, they only have ADC. So these are all pins which are capable of inputting analog voltage. This one as well, this one, this one, this one, but only very few pins have DAC. So basically only these two pins are analog, and they are capable, they can be configured as analog, and they are capable of outputting analog voltage. So this specific microprocessor only has two DAC channels, and those are on pin PA4 and PA5. Another very important issue, almost a trap for beginners, is this is an Arduino. It's a very common kit for beginners in electronics. Uh, it's very easy to program. It has a very vast community of people, and there's very nice documentation about it. But there is a little bit of trap regarding the analog pins, because we can see the Arduino does have analog pins over here, A0 up to A5, so 6 analog pins. And all of these pins have an ADC, meaning that they can process analog voltage, they can input analog voltage, but this chip doesn't have it doesn't have DAC. So that means it's not able of outputting analog voltage. It doesn't have DAC at all. We've seen before with the STM32 chip that it also just had two DAC channels. This one doesn't have any. So it cannot output analog voltage. But if we look in the documentation, there is this command called analog write, and you can use it very easily. And it sort of acts as it can output analog voltage, but it cannot actually. This can be quite confusing. What it does is that it outputs a digital voltage, but it outputs a PWM. This is a pulse width modulation. What the pulse width modulation is, it's just a square wave. So this would be the time and this would be the voltage axis. And what PWM voltage is that it is such a square wave voltage like so, meaning there is only logic high or logic low, nothing in between. And if you call analog write and you put some value in the analog write, you can see that uh, this is the syntax of the analog write command. It accepts which pin should output an analog voltage and what voltage should that be? Well, what you are actually doing is that if you put some value over here, this value doesn't set an analog voltage on the output. It just sets the duty cycle. So if you place some low value, it will perhaps look something like this. It sets the on time of the pulses. That's why it's called a pulse width modulation. You are setting this pulse width of the square wave voltage. But this is still a digital voltage. It's only ones and zeros. If you put some very, let's say, high value in the analog write command, you're gonna be generating something like this. You can see that the duty cycle went up drastically, and the pulse width is now even larger. So this is what you're actually doing if you're calling analog write command on an Arduino. So you are not generating analog voltage at all. You are only generating the PWM. And it can be even more confusing because if you then take a digital voltmeter and you measure the voltage on the pin, you will actually see the average voltage of these two of these pulses. So if we check the voltage on the pin while the duty cycle is very low, we may actually see that there is some very small analog voltage, right? So in this case, for example, the average voltage is this one, and this is what we would measure. If the duty cycle is higher, the average voltage is, for example, here. And again, this is what we would measure with a voltmeter. It's not going to show that there are very quickly changing ones and zeros. It will measure the average. So it can be very confusing. And of course, if the duty cycle is very high, we may actually measure this average voltage. So this is just a simulation. You can see here we have the PWM source. It's just a square wave source voltage. We can see it here. These are the pulses. It's either 0 or 5 volts. 0 or 5 volts, logic high or logic low. And what we did here is that we added a low pass circuit, which is just a low pass filter from a resistor and a capacitor. And what this circuit does is that it averages this square wave. So we can see here, this is the average voltage. This is the voltage on the capacitor. And it should not surprise us that with 50% duty cycle, we have 2.5 volts because this is the average. So half the time it's 5 volts, half the time it's 0 volts, meaning the output voltage, the average voltage is 2.5 volts. So this is how you can actually use the analog pin as a real analog output pin if you uh, average average the PWM with a capacitor and a resistor like this, right? So if we change the duty cycle, if we put the duty cycle much lower, well, this is gonna take some time because the capacitor is big, so it's gonna take some time before the capacitor shows the correct value. So let's speed up the simulation. We can see that after some time, the average voltage is much, much lower because the duty cycle has changed. So now we have 0.5 volts on the capacitor. So this is the disadvantage of this circuit because it takes some time. It takes some time before it settles, right? So we can change the duty cycle, but it will take quite, you can see we changed the duty cycle drastically, but it will take some time before this capacitor tells us the correct average. Of course, we could lower the capacitance so that the circuit acts quicker, but then you can see that we have this slight ripple voltage on the capacitor. So if we make it even lower, we can see it even clearer that there is this voltage ripple. So the capacitor needs to be as big as possible so that the voltage is nice and smooth. But then the trade-off is that it takes longer time for this circuit to settle. Now there is also another problem, and that is if we want to load this circuit. Imagine that we want to drive some, let's just put a resistor over here. Let's put a 100 ohm resistor, and let's have a look at the output voltage now. Well, what we see that the voltage has drastically gone down. Well, that is because we have 1 kilo ohm resistor here. So if we put a 100 ohm resistor here, of course, this circuit doesn't have enough power to power this 100 ohm resistor, so the voltage will go down. So this voltage no longer tells us the correct average voltage of this PWM modulation. So what we could do is that we add an operational amplifier and we create a buffer again. So let's create a buffer just like so. And let's speed up the simulation so that the capacitor settles. There's a big value of the capacitance, so let's speed it up. And now the circuit is loaded. Of course, the operational amplifier does not possess very high load on this circuit, but it can output very high power on the output. So the voltage on this resistor is now going to be, of course, the same as the average voltage over here, but it can deliver the current needed. So this is how you can change an analog pin of an Arduino so that it can output analog voltage, a real analog voltage as well. Of course, you cannot expect much of this circuit because there are two big limitations. First of all is that the PWM has some resolution, so it cannot output just any duty cycle. There are the smallest possible changes of duty cycle which are dependent on the resolution, and a resolution of the PWM on the Arduino is not very great. Also, the frequency, the output frequency of the PWM on Arduino is very small. It's only 490 Hertz. We can see that over here. Frequency of PWM 490 Hertz. So that's very low frequency. So if you want to create some very fast changing signals, well, that's not going to be possible, of course, especially not because of this high capacitor over here if you're gonna configure, if you're gonna build a circuit like this. Now, so this is a problem. And by the way, you can tell immediately if a microprocessor has an ADC or DAC just by looking at the datasheet. So if we look at the datasheet, if the chip has an ADC or DAC, it's going to be written right on the first or second page of the datasheet. So we can see immediately that the Arduino chip, the ATmega328, has ADC. It has 10-bit ADC, but we see no DAC over here anywhere. So we can immediately tell that it doesn't have a DAC. You're also going to see very quickly in all the data sheets, if we look at the ADC, what's the resolution of the ADC. You can see here that it is 10-bit. So uh, that's going to be one of the first information you're going to find about the ADCs and DACs. In fact, you will see the resolution. Now, there is a problem with the resolution because the higher the resolution, usually the ADC gets slower. This also happens with the DAC, of course. So it's always a trade-off between the resolution and the speed. So if you are expecting like 16-bit ADC to sample a signal million times a second, well, that's going to be very, very expensive ADC. For example, Arduino has a 10-bit ADC, and the sampling frequency of the ADC is somewhere between 9 and 10 kilohertz, if I remember correctly. So you can uh, sample a signal with 10-bit resolution, and you can do that 10,000 times per second on an Arduino. Of course, on chips like the STM32, this is going to be way, way better. They are configured, they are built such a way that they are better than these ATmega chips. And their ADCs are usually, you can see over here, 12-bit, so that's 2-bit better resolution, 1 mega sample per second. So that means we can use a sampling rate of 1 megahertz. Okay, the last important thing that I would like to mention regarding the analog pins is that if you have an ADC, just like so, so this is a pin with an analog to digital converter, the ADC will act as a very high resistance, so it will not draw any power from whatever circuit you have here that you are trying to sample the voltage on. But there is a problem because usually it will act as a very high resistance. But during the sampling time, most ADCs will actually, for a very brief moment, draw some current. And this current may not be that small. So you can basically imagine that there is a sort of switch over here and lower resistance. For example, if this is like 1 mega ohm, this would be, let's say, 1 kilo ohm. It's going to be several, or at least a couple orders of magnitude lower resistance. So during the sample, this resistance will actually dominate and it will load the circuit. So this is why when you are using an ADC, I always recommend to put just a very tiny capacitor over here, a very tiny one, for example, 1 nanofarad, just so that the voltage doesn't drop, so that the ADC has somewhere to draw the current from. So this is also some issue that you can come across. So use just very tiny capacitors when you try to sample a signal from an ADC. So let's now finally have a look at a digital pins of the microprocessors. And as we've already said before, digital means that there are only ones and zeros, only logic high, or only logic low. So what's going to tell us if a signal is logic high or logic low? Well, certainly the voltage, but uh, from what threshold we can say that a signal is logic high, and from what threshold we can say that it is logic low? Well, this actually depends on the microprocessor itself. So let's have a look here. This is the STM32L, and we can see here in the datasheet in input-output port characteristics that input low-level voltage is a maximum of 0.3 times the supply voltage. So uh, let's have an example. So they told us it's 0.3 times VDD or VCC, and let's say that VCC, let's say it's 5 volts, right? So 0.3 times 5 volts, that is 0.3 times 5, that is 1.5 volt. So this is the maximum voltage that the processor will still see as a logic low. Of course, any voltage below this voltage will automatically be logic low. Now, for the logic high, we can see that this is 0.5 times the VDD plus 0.38 volts. So 0.45 times VCC plus 0.38 volts. So you can see it is dependent on the input voltage, of course. So 0.45 times 5 volts, that's 2.25 volts. And we must add this 0.38 volts. So that's 2.63 volts. So anything above this voltage is going to be considered as logic high. What about if the voltage is in between? Well, then it depends on the previous state of a microprocessor. So basically, of the pin, of course. So if this is the time axis, this is the time axis, wrong color, and this is the voltage. Well, then if we're gonna have some voltage that is changing, let's say, such a way, then we have these two thresholds. These 1.5 volts, so let's say that is somewhere here. That is the low threshold, 1.5 volts. And we're gonna have a high threshold, the 2.63 volts, which is over here. So this is the high threshold. All right. So let's look at what's gonna happen. I will use this color, for example, to mark the state of the output pin, or the input, of course, depends. So uh, if we're going to plot it, we have to see what is the state of the microprocessor before. So here we have voltage that is clearly low. So the output will be low. And then what must happen is that the voltage, in order to change state of the pin, we must um, we must cross this high threshold. So all the way here, it will cross the threshold, and the logic will now be high, considered as high. Now the voltage falls below the high threshold, and nothing will happen until the voltage reaches this low threshold. So somewhere here, we've crossed the high threshold, but nothing will happen until here, where we are back in the low threshold. And again, the pin will be low until we reach the low threshold, and then nothing will happen again. Because again, we must reach this high threshold. So the pin will be low all the way up to here. So you can see the pin sort of remembers the state of the pin, and it doesn't change until the next threshold is reached. So in between those two thresholds, where the voltage is sort of undefined, it matters to what was the previous state of the pin, right? So now the pin would be high all the way up to here, and it would be low all the way up to here. So this sort of undefined region is what we call the hysteresis. The hysteresis. And it sort of acts as a immunity to EMI. I've already said that the digital pins are not so sensitive to EMI, but consider that if we plot this again, consider that we have a voltage that changes from logic 0 to logic high. But during the change, there are some, oscillations that can happen. So the voltage is going to look, somewhat like this. It will ramp up with these sort of oscillations. And then it will finally settle at logic high value. Well, thankfully, we got these logic thresholds. This is the logic low threshold, and this is the logic high threshold. So the state of the pin is going to be low, and it's going to be low until here, where we reach the high threshold. So even though over here we have certainly crossed the low threshold, we've reached beyond the low threshold, nothing will happen because we must cross the high threshold first. So it sort of acts, this hysteresis sort of acts as a immunity to EMI. Now, digital pins can also be configured as either input or output. And this time, I have never seen a pin, digital pin, where it wouldn't be able to do both. So we've seen before with analog pins that some analog pins are only input and some are only output. Digital pins can always handle being configured as input and output pins. So if we have a digital pin over here, let's call it D0, a digital pin in an input state will act as a big resistor, right? So this will be a big resistor, let's say 1 mega ohm, a very big resistor, and this will go back to the microprocessor. And if you connect something here to the digital pin, if there is some circuit over here, well, this 1 mega ohm resistor is not going to load your circuit very much. So that's not a problem. Now output, in the output configuration, basically what you are doing is that you are adding transistors to the pin. So in the output configuration, we could see that there are two transistors, just like so. There would be one transistor here. I will draw MOSFET transistors, and here's the ground. And there will be another transistor here. And this transistor will connect to the positive supply rail. So now, if you configure the output for logic high, well then this transistor is going to be turned on and this transistor is going to be turned off. What this will do is that whatever is connected here to the digital pin, it will connect this transistor and the current can flow this way. Now, if you do the opposite thing, if you configure this one as turned on, meaning that you will configure logic low, well, this one will be turned off. And now this transistor is going to be open, and so the current will flow this way. right? So the output state of a digital pin basically either sources or sinks the current. This configuration is called a push-pull configuration because it either, pulls the current or pushes the current to the digital pin. And this circuit can only be logic high or logic low. There is nothing in between. In some certain configurations we will see later, the situation can be a bit more difficult. A push-pull configuration is a high power drive, meaning it can deliver sufficient current for most applications. The current it can provide usually is in tens of milliamps, which should be more than enough for what microprocessor should do. Actually, if you want to connect, for example, an LED to such circuit, you will even need to add a resistor because the drive is that strong that it would destroy the LED if it was connected um, directly to ground or to the positive supply rail. So if we connect LED, sorry, the opposite way, like so, for example, and one LED that will be connected this way to positive supply rail. If the circuit is logic low, what will happen is that this LED will light up, this one, because the current will flow from the supply rail through the resistor to the transistor over here. Of course, if the circuit is logic high, well then the situation will be different because this LED will light up. Of course, this is because now this low side transistor is turned off and this is turned on, so now the current will flow this way through the LED. Notice that the state of is either high or low. The LEDs, it will never happen that none of these LEDs is lit up, or it will never happen that both of these LEDs is lit up, of course. So only one LED at a time is turned on. So let's have a look at a different configuration. This configuration is actually completely the same. Uh, let me draw it the same way as I did before. There is the supply rail. Here is one transistor, just like so. Here would be the digital pin, D0, and here would be another transistor, just like so, and here's the ground. This may look like a push-pull, which it pretty much is, but this is something that we call tri-state circuit, and the only difference is that before, either this transistor was on, meaning this one was off, or this one was off automatically, meaning that this one is on. Well, in tri-state, we can also disable both of these transistors. That's also a possibility in tri-state configuration. And if this happens, well, then this pin will basically be left floating because none of these transistors is turned on. So the current cannot be sourced and it cannot be synced. So this circuit is capable of both logic high, logic 1, it can be capable of logic 0, and it can also be capable of something we call high impedance. You will either see it marked as capital Z, or sometimes there will be just high Z. So in high Z or in high impedance, this is the third state. This is why it's called the tri-state. In the third state, this pin is completely cut off from the supply rails. Of course, there is still this big resistor which goes directly to the microprocessor pin, microprocessor logic. And even though the pin is in high Z state, you can still read the state of the pin. So you can configure the pin as being both input and output. That's possible. Unlike in an analog pin where you could either configure it as input or output, digital pins can be configured to be both input and output at the same time. So that's actually pretty handy if you're using tri-state driver, because it may happen that your driver is in high Z state, but you still want to know what is the state of the pin, because some other circuit may pull the pin low or high depending on what kind of circuit we have connected to the pin. So basically, once the pin is left in high Z or high Z, it means that the microprocessor is no longer controlling the pin state, but some other device that is connected to the pin will actually control the state on the pin, and we still want to know what's the state on the pin, so that's why we still read it. So this is very handy in communications, and we will see one more configuration that's used. It's worth to note that not all microprocessors are capable of tri-state driving. They may only be able to do push-pull. So if this push-pull was actually tri-state in a high Z state, none of these LED would be turned on because the current cannot be synced and it cannot be sourced. Let's talk about the last configuration, which is very common, and that's open drain. Open drain is basically a configuration where instead of two transistors, you only have one. Now, this is the digital pin. Let's call it again D0. And it will be configured as open drain, meaning that there will be only one transistor, the low side transistor, and it will be connected this way. There would be the MOSFET, just like so, and here is the ground. So it's called the open drain because the MOSFET has a, gate and source and drain. And the drain is the terminal that is connected to the pin. Now, open drain configuration can only sink current, or if this transistor is turned off, then it will be in high Z state. So just to recapitulate, push-pull could do either high or low. A tri-state could do either high or low or high Z. And open drain can only do either 0, logic low, or high Z. So open drain configuration is used for usually for communications. So let's say we have a microprocessor here with a digital pin configured as open drain. And then we have another device with the same configuration. There is some kind of pin, and this pin is used for communications, and there is an open drain circuit over here. And this could be some device. It could be a sensor, for example. It could be some sensor that's trying to send data to the microprocessor, or it could even be another microprocessor. We could have two chips talking to each other. It doesn't matter. But there are microprocessor and some device, and they are communicating with each other. So these pins are externally connected together. And what we do is that we connect something that we call pull-up resistor. And this is connected to the positive supply rail. This pull-up resistor is usually in the range between 1 kilo ohm and 10 kilo ohm. I usually use 2.2 kilo ohms. Now, let's have a look at how this works. So if this transistor is turned on, the state of the bus of the communication line, we call that the bus. The state of the bus is going to be logic 0, because no matter if this transistor is turned on or off, If it's turned off, well then, of course, we have high Z on the output, meaning that the pin is pretty much disconnected from the device. Now, if we have logic low, well then both transistors are on, meaning that the state of the bus is going to be low. Now, if the transistor over here is turned off, and this transistor is also turned off, well, then the state of the bus is going to be logic high, because there will be current path through this resistor. So we will see supply voltage on this line, on the bus. Of course, if this other transistor turns on, well, in that case, the state of the bus is again going to be pulled low. So this is a useful configuration because this couldn't be done with push-pull, right? Because let's imagine what's gonna happen if we use a push-pull. So there would be no pull-up resistor. Let's forget the pull-up resistor for now. And let's just quickly say that there is another transistor here. I will just mark it as a switch. There's the VCC and another transistor here. Again, just a switch, VCC. Now imagine if the state of the bus should be low. Well, that means that this transistor needs to be turned on and this transistor needs to be turned off. Okay, but now this device also needs this transistor to be turned on and this one turned off. Because if this one is turned on and this one is turned on, well, then that's a short circuit and it will short the power supply and that's going to be a problem. So if we wanted to use push-pull driver for communications, well, that's gonna show huge problems because this device would need to always be in the same state as the microprocessor. Well, that's not very useful communication. This device sometimes wants to tell something to the microprocessor, and in that case, it needs to affect the state of the bus depending on what it wants to tell. So this would be impossible with a push-pull. So what we do is that what we could do is to use tri-state configuration. Then of course that would be perfectly possible, but open drain is still preferable. Here you can see a diagram of how an I2C protocol works. That's a communications protocol very often used. I'm not going to go into details about how I2C works. That's a topic for another video, but I'm just going to show you that we are using two data lines actually, or two lines. One of them is for the data, one of them is for the clock. The clock signal is very important because the device and the microprocessor, they both need to agree on what transmission speed they are going to use. So usually microprocessor generates this clock signal and it configures the speed at which the bus is going to operate. So both of these devices will now, the microprocessor and the end device is going to use this speed. Of course, you need to make sure that the device is able to work at some speed that you want to use. Some devices may not be able to use very high communication speeds. Now, the SDA line is the data line. So this is where the actual communication is occurring. So you can see when the serial clock turns to logic 1, it turns high. Then here we have serial data turned on. What that means is that the device is, or the microprocessor is going to look at the rising edge of this clock and it will see that the serial data is logic 1. Now in another clock period, we are going to look at what is the state of the bus when the serial clock goes high again. So on this rising edge, we see a 0. And then again, rising edges. Over here, we see 1. So this is 1, 0, 1. This would be 0. This would be 1, 1, 0, 1, 1, 0. right? So this is how the serial communication on the I2C bus works. Notice how every time when we are having logic low on the SDA line, that means the transistor in the open drain is turned on. It could be either this one or this one, depending on which device is transmitting. If this device is transmitting, then this logic low that we see over here is going to be determined by this transistor. If this device is transmitting, then of course this transistor will determine the logic low. I'm just gonna erase this over here. So we have open drain configuration. And every time the data is high, well, then actually no transistors are conducting. It's actually the resistor, which we had over here, that is dictating the state of the bus. No transistor is turned on. This resistor over here is actually, in most cases, the limiting factor to the speed at which our bus can transmit data. Why is that? Well, because every time, no matter how you built your circuit, every time this data line is going to have some capacitance between the data line and the ground. This capacitance is going to be usually very small. It's going to be in the range, in picofarads. It's going to be, for example, 50 picofarads, a very, very tiny capacitance. But when we are dealing with high communication speeds, well, this will become a problem because this capacitance needs to charge and discharge depending on the state of the bus. When it discharges, when the bus needs to be low, this capacitance is not that big of an issue because when these transistors turn on, there is very low resistance between drain and source. So this capacitor discharges very quickly. So that's not an issue. But when the bus is pulled high, meaning that no transistor is on, they are both off, well, what's going to charge this capacitor? Well, it's going to be charged by this resistor over here. And this resistor, as I've already said, can be quite substantial. It could be kilo ohms. So it's going to take some time before even this very tiny capacitance is charged. This time is usually going to be very, very short, but remember, if we want to transmit at very high speeds, even nanoseconds are very noticeable. So what will actually happen if this resistor is too big or this capacitance is too big? Let's have this diagram over here. So what could, in theory, happen is that the SDA line, the serial data line, is going to look more like this. And of course, it will have fast falling edge because the falling edge is triggered by the transistors. Nothing will happen. And now again, when the bus is pulled high, it's going to be pulled by the resistor, which is slow. This is an extreme case, of course, but it's not that far from reality when you deal with very high transmission speeds. It takes some time for the resistor to charge the capacitor. And notice what can happen. This can be a very big issue because we are here on the rising edge of the serial clock. We are reading the state of the serial data line. And at this time, we can see the voltage is somewhere here, which may not necessarily cross the threshold for logic high. So even though we should see logic high on the data line, we can still have logic 0. So the message that we want to send will be distorted. So this is a problem, and there are not many solutions to this problem. Some serial protocols use different approaches. Some use multiple lines for the data. For example, it can use one line for the microprocessor and one line for the device so that they can use push-pull configuration. But I2C uses only one line for the data, and so this problem is pretty much inevitable. You could say, why not just use low resistance here? Why, instead of kilo ohms, why not just use, 10 ohms? That's going to be super quick, probably even quicker than the transistors themselves. Well, imagine what's going to happen if one of these transistors, if the state of the bus is turned low. So one of these transistors is going to conduct, let's say this one. Well, now the current will flow through this resistor, through the transistor. And what's going to limit the current? Well, the only thing limiting the current is going to be the resistor itself. So imagine if we power this from 5 volts, the current that's going to flow in this case is 5 volts over 10 ohms. Well, that's half an amp. No processor on Earth is going to be able to survive this. So the resistor here needs to be quite large, quite substantially large. So you may get away with, 100 ohms or 200 ohms, but you are just going to waste quite a lot of power. It is possible, but you're going to waste a lot of power. So usually, in practice, you are most likely to see something in the range 1 kilo ohm all the way up to 10 kilo ohms. Most microprocessors actually even have this resistor integrated in the chip, and you can buy software. You can either configure it to be disabled or enabled. So that sounds like a good idea, and you can see how to do it here. This is in case of Arduino. You set the pin mode, you say pin number and what kind of configuration you want. So this would be an input pin, which is configured with a pull-up. So here is an STM32 this version of the code. Same thing, you take a pin and you set to be input and you set a pull-up resistor on the output of the pin. Now there is a big problem with this because the resistors, how are resistors constructed? Well, resistors are usually just pieces of wire, pieces of resistive wire. If you want to have a resistance, you take a wire and you just sort of wire around it just like so, and this will have much higher resistance than just a straight piece of wire. But the big problem with this is that microprocessors are tiny. They are extremely tiny. The die of the microprocessor can be 1 by 1 millimeter. It's super tiny. So you cannot ever fit a big resistor in it. And of course, the higher the resistance, you need even longer piece of wire. So it's very hard to integrate resistors on a chip. So even though we can see that the code actually tells us to configure pull-up resistors, we are actually not configuring resistors at all. What's actually happening is that there are no resistors in the microprocessor, but there are current sources. So there is a current source like this. They are much easier to integrate than resistors. So this current source is trying to push some current. So either the transistor here is on, in which case the current source is going to push current to the transistor, but the transistor is open, meaning that the state of the bus is going to be logic low. There will be no voltage. Or, of course, if we use the pull-up resistor integrated, we're most likely not going to use an external one. Now, if the transistor is turned off, then this current source will actually charge this capacitor over here, and we do not need any external resistors at all. So that's nice and handy, but the problem is that these integrated current sources can usually deliver very little amount of current. For example, 1 milliampere, and that is very, very low current. Suppose that we have 50 picofarad capacitor over here, and we want to charge it from 0 to 5 volts, and we have 1 milliampere current source. Well, how long is that going to take? Well, it's quite easy calculation, because the time that this gonna take is just the current. It's the capacitance times the voltage divided by the current. So in our case, that's 50 picofarad times 5 volts. All of this divided by 1 milliampere. And if you do the calculation, you will find out this is 250 nanoseconds. So that's quite substantial time. If we want to use some megahertz, frequencies to communicate, 250 nanoseconds is a very long time, and the bus may not work properly. So that's a big problem with these pull up or pull down resistors, because they are actually current sources and they can only deliver very low current. So I guess the best case, the best solution is just to use a resistor with some reasonable value here, and the value depends on the application. So if you are okay with lower speeds, you can just have 10 kilo ohm here, and you're not going to waste much power. If you need very quick transmission, well, then you may want to settle for lower resistor here and accept higher power dissipation. So you should now have some understanding about GPIOs. We've talked about using GPIOs in analog and in digital configurations. We've talked about different configurations of digital circuitry and the communications bus. And I think you should now have pretty good understanding of the topic, and you should be able to work with GPIOs and perhaps even try some communications, or perhaps some analog stuff, perhaps a work with analog to digital converter uh, that can be very useful for a lot of projects. So I hope you learned something from this video, and perhaps see you in some other video tutorial.